Our next speaker is DiBiagio, a former student of Ralph Peck's, and currently and for the last large number of years busy at the Norwegian Geotechnical Institute.
Ladies and gentlemen, it's a pleasure to be here today to talk about instrumentation to all of you. I'm impressed by the size of the audience. We are ahead of schedule. Can I use a few more minutes? Okay. I have a rather long presentation. It consists of two main parts. I'll talk about the importance of instrumentation, and I'll give some examples. And in between, I'll give some personal reflections about Ralph Peck. Which one? That one? There we go. We'll start. I want to very quickly talk about the importance of measurements. And geotechnical engineers, they work in two totally different worlds. There's a theoretical world where thoughts, ideas, and events can be quantified and calculated to as many decimal points as you like. And the working conditions are comfortable. You're in an office or you're in the academic world. The other world is not so comfortable. This is the practical world of geotechnical engineering, where observations and events can only be described in a general way. Both worlds are extremely important, and we must strive to learn more from both of these worlds. We strive to improve our understanding of the theoretical basis for our work. We must strive to gain a better understanding of the real world of engineering practice, and we must narrow the gap between these two different worlds of theory and practice. Now, how do we bridge the gap between those two worlds? The instrumentation is the tool. Numerical data, the end product of instrumentation and measurement, provides a quantitative link between theory and practice. That's why instrumentation performance monitoring has become so important in our field. Before I go on, I want to just give some personal reflections. Since this symposium is dedicated to the legacy of Ralph Peck, I would like to come with some small comments. Through his teachings, publications, and by all means through his personal contact, Ralph Peck has had a great influence on the professional careers of many students and geotechnical engineers worldwide. So I'd like to take a few minutes to illustrate by pointing out the key role he has played in my own professional career, and I would like to point out the sequence of events that brought me here today to participate in this special session. The road I took spanned between two continents. There is no road. However, a few years ago when Google started putting maps on the internet, you could get driving instructions, and I tested it. I wanted to go from the Waldorf Astoria Hotel in Manhattan to Oslo. I got detailed instructions to go down to the Battery Tunnel, and then it said drive to Kristiansand at the southern tip of Norway, and then I got detailed instructions how to get to Oslo. So beware of what you read on the internet. So I put in a road with a bridge, and it's a beautiful road and bridge on the coastal highway on the west coast of Norway. I hope some of you can come and visit it someday. The road I took, it started with my interest in instrumentation, and that started at 1952 at Penn State. I had a part-time job in the structurals division. I had to mount 250 electrical resistance strain gauges on a large model of a steel bridge. It was a terrible job, but I didn't lose my interest in instrumentation. The next step was a graduate research appointment at Princeton University under Professor Chebotaryov. At that time, Chebotaryov and Terzaghi did not agree on how to design anchored bulkheads. So at Princeton, I was working on instrumenting model anchored bulkheads and also large-scale measurements on anchored bulkheads in the harbors of New York and Galveston, Texas. The next stop on my road was Norway, a Fulbright scholarship to spend 1 year there, and they started working on the Oslo subway, and I got involved in instrumentation of braced excavations, first as a Fulbright scholar and later as a part-time engineer. I met Ralph on that road I took. I met him in October 1959. He had been invited by the city of Oslo to come to Norway and comment on the plans for building the new subway. Now, I was given the honor of showing him the excavations. The city of Oslo provided a Mercedes car, a chauffeur, and we spent a whole day driving around the city looking at excavations for buildings and for the tunnel. And it was a long day. And at the end of the day, he said, and I'm quoting it, "If you want to pursue a degree in PhD, send me a postcard." That was quite a compliment. And I didn't send him a postcard, I sent him a letter in 1962. And in those days, it only cost 3 cents to send a letter, so I could afford that. So the next step on the road was graduate studies at the U of I. He was my advisor. And although I had a lot of experience in instrumentation, I wanted to try something different in the nice, clean, theoretical world of geotechnical engineering. So I elected a numerical analysis of a problem related to excavations. I solved the area stress function of fourth order differential equation. And it took me 2 boxes of IBM punch cards and a computer that had 2,800 radio tubes. That was technology in 1962. The next stop on the road I took was back to Norway. And this is a point where Ralph Peck had a tremendous influence on my future. When my thesis was finished, and he looked at it and he said, well, no theory or mathematical model can be considered satisfactory until it has been checked by actual observations. And I think that comment of Ralph, and it's also a quote that you read in the literature quite often, that convinced me to go back to Norway, and I did that in 1964, and I've been working there ever since on probably 100 or 200 different instrumentation problems. And during that whole period since then, for 44 years, I've had a close personal friendship and professional friendship with Ralph Peck. And the same goes for our whole institute, the Norwegian Geotechnical Institute. The last event, the last stop on the road I took to get here today was 3 years ago, where I received an invitation to present a paper, and I was indeed honored, and of course I accepted. But when I accepted, I said, at the time I was 78 years old, and I said, well, long-range planning is somewhat uncertain at this time. So I'm very happy that I was able to come here 3 years later at age 81. The topic I chose for my paper, the importance of field measurements, for me it was an easy choice, but a difficult task to implement. My paper is a collection of instrumentation case histories, and I had a plan A and a plan B to do that. Plan 1 was a traditional, you take 1 or 2 case histories and go into great detail. Plan B, I wanted to show a larger number of examples to illustrate the variety of instrumentation projects. The scope of my paper, I elected Plan B, many examples. I ended up with 22 of them, and I didn't want to discard any of them. And how do you present 22 papers in a 20-minute presentation? The only way I could do it was to use the 1-page summary that we've heard so much about. And that was something Ralph demanded of his students in the course CE 484. and he insisted on it. And there's one example where a graduate student who had worked many years in engineering attended that course, and on his first report, he submitted 20 pages. And Ralph said 1 page. He wrote it again, and he submitted 12 pages, and Ralph said 1 page. And then he wrote 4 pages, and he said, I can't reduce it anymore, and Ralph said 1 page. And he ended up with 1 page. So my presentation in the proceedings consists of 22 one-page summaries. This is the content, the background and description, factors that influence the design, the scope of the instrumentation, the most significant results, and then a reference. And here's what one looks like. At the top, there is a laser here. Well, anyway, at the top, there's a sort of a summary, the category of the measurements, the main benefits. No, the main, I can't read my own writing from here. And then the main conclusion. And this is just one example, description of the project here, factors that influence the design, something about the instruments, and then the main findings of it. So my dilemma today is how I'm going to present 22 case histories. The allotted time I have is 17.5 minutes, and it was stressed that I had to keep within 17.5 minutes, and I don't need the University Iliac computer with 2,800 test tubes radio tubes to tell me how to calculate that this is an impossible task. So what I'm going to do is to just flash through each of these examples one at a time so you can see. I'll include pictures and some simple diagrams from each of these one-page summaries, and in a few of them I'll add some explanatory comments. So if you see something of interest in these 22 examples, then you will have to go to the proceedings and read the details. And my presentation will stop regardless when time is equal to 17.5 minutes. I think that was I was told. Now I'm going to present them one at a time so you're not distracted. The first one was in 1955. It was the first field instrumentation project carried out by NGI, and I did it when I was a Fulbright scholar. It's a simple braced trench in weathered marine clay, which is the principal surface deposit in Oslo, and they make many of these trenches for installation of utilities and so forth. So it was important to get design information for it, and also the effect of freezing on such an excavation. That was number one. Number two was one of the key excavations for construction of the subway, where one had to excavate to a depth of about 11 meters. The critical depth of excavation there was a little over 4 meters. So the procedure adopted was to excavate down a certain level and fill the trench with water and excavate down to the final depth underwater. And the instrumentation was traditional displacements, a lot of pressure transducers and strain gauges on these strutting and sheet piles. And the project was carried out successfully. We also found out that we did not need the one level of struts that had to be placed underwater. Number three is a large in situ shear box testing device. This monstrous thing was built. It's a self-boring shear box that could do a direct shear test on a sample in situ 1 meter in diameter. And it was used in the 70s at 4 sites in Norway and 1 site in Sweden. 1 meter in diameter. Number 4 is an example where you have an unexpected problem and you need some instrumentation. This was a rock-filled dam with very little instrumentation, and during the first filling there was leakage detected downstream. Well, instrumentation was used, pore pressure sensors were used in boreholes to find out what was the cause of the problem, and then to check the effectiveness of the remedial action that was taken to reduce the leakage. The next one is a case of a small dam that had to be built where there was no material for a fine grain, no fine grain material for the core. So the core was made by injecting hot bitumen into thin layers of gravel, as shown in the picture. And the problem was that for the thing to work, the pressure in the bitumen in the pores of the gravel had to be higher than the water pressure in the reservoir. So we developed instruments to measure pore bitumen pressure. And if you want to know how that was done, look at the case history. This is another interesting example, which was research and development. And that was number 6. That was in 1972. A strip loading to do some research on the strength of the underlying soil. And it was calculated that the failure would occur based on the field vein at a height of 3.5 meters. When it got to 3.5 meters, it didn't fail, so they kept filling and filling and filling, and we ended up with a pyramid and no more place to place fill. And the height was over 6 meters, and it had a calculated factor of safety of 0.57, and it stood for 2 years without failing. After 2 years, we excavated a trench out on the side there and caused a failure. Now, if you want to know why, you have to read the paper. Number 7 is related to the use of the slurry trench wall in soft clay. It had never been done before, and the problem was, what density of the slurry do you need to stabilize the trench? And we made a full-scale test excavation and started with a slurry, bentonite barite slurry of 1.24. We reduced it down to 1.1 and observed it, reduced it down to 1.0 plain water and observed it. And we found out from the measurements that we could use them without using slurry, just using plain water to stabilize the trench, and that was done for construction of a deep combined railway tunnel for the subway and the rail line in also a very deep excavation. Number 8 is a simple full-scale test of a retaining structure for a company that manufactured artificial fertilizer. We didn't know how to calculate the earth pressure due to artificial fertilizer. The client was going to make 30 very large storage bins with prefabricated elements, and he wanted a full-scale test. So a test was run with pressure transducers and strain gauges to verify the design. Number 9 was a test on an anchor block in connection with a study for building floating bridges to cross the fjords in Norway. One constructed a block of reinforced, the aggregate was iron ore to make it heavy. It was a block 130 tons, lowered to 460 meters of water in the fjord, and there was a hydraulic system to measure settlement in order to check the predictions of the settlement from laboratory tests. And it was monitored for 1 year, and after 1 year, the arm that holds the settlement reference device hit the container on the sea floor, and the measurement stopped. But it was very successful. The next one is a traditional instrumentation of a rock-filled dam in Norway, heavily instrumented because it was the first one over 100 meters high. This dam is 129 meters high. It had a lot of traditional instrumentation. The principal measurements were pore pressure. Because of the sloping core and the thin core, if the pore pressures got too high, there could have been a failure. There were provisions for increasing the safety of the dam by adding more material on the upstream slope, but the measurement showed it was not necessary, and one saved a lot of money and one saved a lot of time in construction. Now we're on number 11, which is a very unusual one, measuring the contact force between ice of a moving glacier on bedrock. The contact pressure between the glacier and bedrock, on the plane surface of the rock and on an anisotropic or a device with 3 cells placed on the surface of the rock under the glacier. Now, if you want to know how you get under a glacier to do that, you have to read the paper. The next one is the oil age in Norway in the 70s and 80s. Here we see one of the gravity-based structures on the left. It's compared to the United Nations buildings in Manhattan, and it was installed in 149 meters of water. They're constructed in a dry dock, floated out in deep water in the fjord. The whole structure is built, the deck is put on top of it, towed out to the sea and set on the sea floor without damaging it. And it generally requires from 100 to 200 instruments to monitor all of that, and also to monitor the structure during storm periods. Measurements on that structure are still going on. There was a crew out there last week reading the instruments. We're on number 13 is we have a research center for studying avalanches, the dynamic properties of avalanches. There's some structures built in the avalanche path. You see one of them measures the contact pressure, and it survived several years, but after a few years it died. Can I continue? Okay, I'll go quickly through the next ones. This was a very large-scale test of a penetration of a concrete wall offshore. That particular platform had 1,400 linear meters of concrete wall that had to be penetrated 23 meters into the sea floor. The base of the structure is like a gigantic cookie cutter that had to go down 23 meters. And the tests were carried out successfully, 2 tests offshore and 220 meters of water, and the comparison between predictions and actual measurements were extremely good. Number 15 is a dam with an asphaltic concrete core that is relatively thin, and you have to have the core must not have different displacements in the surrounding soil. So the instrumentation is to verify that the core, which is asphaltic concrete, is moving to compatible with the surrounding supporting fill. This is a large-scale test of a suction anchor, and it was very interesting in that the predictions were done before the test and given to the client. The client put them in a safe, and after the tests were performed, the client opened the safe, pulled out the envelope with the predictions, and there's a tabulation. The predictions agreed within maximum 6%, which was extremely good. Number 17 is a problem you have on some subsea pipelines. They're operating under very high pressure. This one has 2 pipelines bringing gas from the North Sea to Germany, and they have to change direction near the tie-in point to Germany in what's called a connection, a caisson offshore. And due to that change in direction, the pipes are 1 meter in diameter. The operating pressure in gas is 165 bar. That generates a force of 25,000 kilonewtons on the pipes and the structure. That's 2,500 metric tons. And that induces large stresses in the pipes, so we're monitoring the stresses in the pipes on that. Number 17 is a large tailings dam in Poland, the second largest one in the world. It's essentially circular in shape, 5 kilometers in diameter, and it's somewhat unstable, very deep shear plains, but the observational method is being used to control the rate of constructing that dam and the geometry of the dam. There are over 300 vibrating wire piezometers and 70-some deep, very deep inclinometer installations to monitor the data needed for the observational method. Number 19 is just an example of the use of fiber optics in our monitoring work, which is becoming more popular. It happens to be a bridge monitoring five old bridge beams that are failing because of fatigue, and each one of those beams is 950 meters long. 5 of them are monitored. Each scan of the data system gives you 50,000 strain measurements. Number 20 relates to drop anchors that are used offshore. These are tests of a typical drop anchor might weigh from 50 to 100 tons. They're lowered to a certain depth and then released to go free fall, and there's a flight recorder attached to them to measure acceleration, velocity, pore pressure, and depth of penetration. Number 21 relates to piles for offshore wind turbines. And in the European community, they expect by the year 2020 there will be 9,000 of these installed offshore. So there's instrumentation needed to monitor the piles to simplify the installation procedure. Number 22 is a recent project started in 2010. It's related to a connection between the southern tip of Denmark and Germany, a 19-kilometer long connection. It may be either a submerged tunnel or a bridge. On the German side of it, there's swelling clay, so there was some special instrumentation designed to do a full-scale test offshore to get information about the effect of excavating over the swelling clay. And we have, for the first time, very good measurements of the heave and the negative pore pressure set up when you do such a case. That is the last example. And I will end it with the word of caution from Ralph Peck that he prepared for the ICOLD conference in the year 2000. He said, "There's a danger that instrumentation may be discredited because of indiscriminate use." And I'll add one more slide. Lord Kelvin has pointed out why measurement is important. He said when you can measure it and express it in numbers, you know something about it. And I'll add one final slide about the real world of geotechnical, one of the worlds of geotechnical engineering. And I thank you very much for your